Hi everyone, and welcome to this lecture titled Batteries and Cells. So this lecture has quite a few pages to it, so download the PDF, it'll be very handy for you. But you've most probably heard of batteries before. In fact, if I was to hold one of these up, or perhaps one of these up, you would say, oh, those are batteries. Well, the interesting thing is, the technical or the proper name for these is actually a cell. So one single one of these, which again we normally call a battery, is actually called a cell. When we put multiple cells together, we actually call them batteries. So in this case, this would be called a battery because it's got multiple cells all connected together. However, as I've got it here in the notes, generally if you talk about a battery, people know what you're talking about, so we really don't need to go crazy with saying, no, you cannot call that a battery, because it's perfectly fine. Anyway, that's what this lecture is about. So have a look what I've got here. Let's get a bit bigger, let's go green. So I've got all types of batteries or cells, if you like. So this one over here, this one is a 9-volt. In fact, you can call that one a 9-volt battery because inside a lot of these 9-volt batteries are 6 of these AAA batteries or 6 AAA cells. And we'll see how they connect that up a bit later. So that one gives you 9 volts. This one here gives us 1.2. This one's 1.2. This one's 1.5. We've got this one at 12 volts, 1.5. This is 3.7 volts over here. We've got these little coin cell batteries that give us each 3 volts. So batteries are made in all sorts of different sizes, out of all sorts of different metals, out of all sorts of different chemicals within there that we call the electrolyte. They're made in different packages. They're made to give us different voltages. They're made to give us different amounts of current capabilities or capacities. Some are used to start cars. Some are used just to power remote controls for your television. There's all sorts of batteries for all different sorts of purposes. Now the interesting thing is, I guess, is the operation of each battery or each cell is pretty much all the same. So we're going to go through a really simple cell. We're then going to have a look at what happens when we connect them up to each other in different ways, and we should have a bit of fun with this. Okay, let's have a look at this first. A very simple cell. So you can actually make a very simple cell or a very simple single battery. You just need to get 2 different metals. In this case, I'm going to use the example of using zinc right here and some copper. So we get this zinc and we get this copper and we put it in some kind of what's called electrolyte. In this case, I'm going to use an electrolyte which just needs to be some kind of liquid, or it could be a paste that can conduct electricity. So in this case, I've got zinc, that's one piece of metal, copper, that's another piece of metal, and there I submerge them in sulfuric acid. Now again, this is a very simple, basic explanation. Pretty much all batteries operate on this principle. But what actually happens is, just let me grab something a bit smaller here, we start to get, once we submerge these in here, we actually get the zinc dissolving within the sulfuric acid solution. As the zinc dissolves, we start to get electrons building up around the zinc terminal. The copper, when that's immersed in the sulfuric acid, we start to get the copper also dissolving in here. The copper starts to release electrons into the solution. These electrons actually get attracted over to the zinc cathode. So it builds up even more electrons over here. At the same time, just due to the sulfuric acid mixture, we start to release some gas in the form of hydrogen. So we need to make sure that gas can escape. But because the copper anode is losing electrons, it now has more protons than electrons, so it starts to build up a positive charge. And because the zinc, in this case, the cathode, is getting electrons, it's now getting a negative charge. So we start to get a difference between the two. This is negative and this is positive. Now this is a very basic, simplistic operation of how cells actually work. And it's pretty much what's going on inside this thing. It's pretty much what's going on inside this thing. They just use different chemicals and different metals. But the key thing is we have some kind of electrolyte, solution, paste, liquid. We put 2 different metals in there. One of those metals is going to lose electrons, and those electrons will go over to the other metal which will gain those electrons. One of those metals will become negative because it gets all the electrons, and the other one, because it's lost electrons, will become positive. Alright, so what happens when we connect an external circuit? So if we were to get one of these cells and then get a resistor or an LED, light bulb, something like that, and connect it to it, we've now got a complete external circuit. So in that case, we're going to get, so the electrons are going to migrate their way over to the negative terminal, which is made of zinc in this case. So internally in the battery, the electrons actually go from the positive terminal to the negative terminal. Externally, they go from the negative to the positive. So the electrons are traveling through here, around like that, and back this way. And they just keep following that cycle. So we keep this circuit connected, they'll keep going around, and eventually we're going to eat away with our metals inside this inside the solution, and the battery will completely be dead, and we'd have to throw it out. So I did make a note in the very first page that there's two types of batteries. There's primary batteries or primary cells and secondary cells. The difference between a primary and secondary is that, so this for example is a primary AA cell right here. These ones you cannot recharge. So once they're dead, you just throw them out. But these types of cells, so we've got rechargeable ones, which you may have heard of lithium ion before, or nickel metal hydride, or what else have we got? Lead acid batteries are another one, which you commonly use in cars. We can actually reverse the chemical effect in this thing. So when we connect up a power supply, so I guess I could show you quickly just the recharging process. If we were to connect a power supply to this thing, so that we can force current to go in the opposite direction, this way through it, we can reverse that chemical effect. Once we reverse the chemical effect, we can enable so the battery is fully charged again, and then we can go back to powering a circuit where the electrons again go off of the positive anode plate onto the negative, and they go through the circuit. So that's a very basic run through of your rechargeable batteries. Okay, so primary cells cannot be recharged, secondary cells, they can be recharged. Alright, characteristics of cells. A very popular cell these days is the AA, so just like this one here, and even the AAA, which is a bit smaller. There are commonly two characteristics to take note of with any cell. The voltage, which is given in volts, and the current capacity, which is given in milliamp hours, commonly. If we're talking about big car batteries, they're generally in amp hours, so AH instead of mAh. So let's check out this particular one that we've got right here. So this guy is giving us 1.5 volts, and it's rated at, it's got a capacity of 1000 milliamp hours. So that means if we were to connect up a voltmeter between there and there, the voltmeter would read 1.5 volts. Now, what does the 1000 mAh or milliamp hour mean? Well, that means if we were to connect it to a circuit, well, I've actually got one drawn down here, so let's go with that one. If I was to connect it to this particular circuit, so we've got a resistance of 1.5 ohms. In fact, let's do the calculation so you see I'm telling the truth here. 1.5 volts divided by 1.5 ohms, because there's my resistance, 1.5 ohms, we get 1, and that is 1 amp. We've got 1 amp of current flowing in that circuit. If we convert that to milliamps, it's 1000 milliamps. Now this particular cell is rated at 1000 milliamp hours. That means if you connect it to a circuit that is drawing 1000 milliamps, it will last for 1 hour. If we connect it to a circuit that is only drawing 500 milliamps, it would last for 2 hours. So the capacity is measured in milliamp hours, and from this we can work out how long the battery will last in any type of circuit that we're going to put it in, as long as we can figure out, well, how much current is it going to take. Okay, what about these ones? How long will these cells last? Okay, so let's do a couple of calculations here. I'm just going to change to that. So what do we need to know? We need to know the resistance, the voltage to find current. So the current in this circuit is going to be 1.5 volts divided by 3 ohms. Let's do the calculation. 1.5 divided by 3, and we get 500 to the negative 3, which means 500 milliamps, so half an amp. So how do we figure out how long it's going to last? Well, we know it has a capacity of 1000 milliamp hours, so we're going to go 1000 milliamp hours and divide it by how much current we're actually drawing, which is 500 milliamps. Do it on the calculator, so 1000 exponential negative 3 to give us milliamps, divided by our 500. exponential negative 3. And we get 2. That is going to last for 2 hours at that rate. Okay, what about this one? Resistance has gone way up, so hopefully you can see the current is going to go way down compared to our other calculations. Total current equals the voltage, which is 1.5 volts. There it is, 1.5 volts, divided by our 10k resistance. What does that equal? 1.5 divided by 10 exponential 3 to give us 10k, 150 to the negative 6, which means that's 150 microamps. So that's not very much current at all. How long is it going to last? Well, it's rated at 1000 milliamp hours. So 1000 milliamp hours divided by the amount of current we're actually drawing, 150 microamps, should last for quite a while. 1000 exponential negative 3 to give us milliamps, divided by our 150 exponential negative 6 for micro. That's going to last 6.67 hours. Oh, sorry, 6.67 times 10 to the 3. So that's actually 6,667 hours. 0.67. So 6,667 if we just round it hours. So as long as you draw very little current, you can make your circuit last for a very, very, very long time. So in fact, you may have seen these sorts of batteries before, these types of cells right here, 3 volts, commonly used in watches, or maybe these ones right here. So how long does your watch battery last? Well, it lasts, I don't know, a year or even more than a year. That's because the circuitry inside your watch is not drawing very much current, so it can actually last that long. And the good thing is, because they actually printed on the battery in this case, or the cell, so even I keep using the term battery, which is fine, 2,300 mAh. So this one has more than twice the capacity of this one here. So it's going to last more than twice as long as this, more than twice as long as that, which is good news. Okay, so now let's talk about actually making batteries like this. To make batteries, we get multiple cells and we connect them together in some kind of configuration. So batteries are made up of multiple cells. We can connect cells in series, parallel, or a combination of the two in order to meet our requirements. Connecting cells in series increases the total voltage, but the current capability stays the same. So for this particular example, we've got a whole bunch of 1.5 volt cells. We connect them in series. We then get 1.5 plus 1.5 plus 1.5. We get 4.5 volts total, as you can see over here. Let's make this a bit bigger. 4.5 volts. Now, if we were to connect that to a resistor that is 4.5 ohms, we'll find out that we get 4.5 volts divided by 4.5 ohms. The amount of current we're getting is 1 amp or 1000 milliamps. Now, when we connect them in series, we do not increase in any way the total current capacity of the cell or of the battery. It's still going to last for an hour. However, we've now got 4.5 volts instead of 1.5. Now, the other way we can do it in this case is connecting them in parallel. In parallel, we just need to get multiple batteries or multiple cells like this. We get 1, 2, in this case we get a third one, and we just connect all the positives together, all the negatives together. Now this time you don't actually increase the voltage at all, it stays at 1.5 volts. The only way you can increase the voltage is connecting them in series. But the good thing is, we increase the total current capacity of the battery itself. So this time, if we've got 1000 milliamp hours plus 1000 milliamp hours plus 1000, we actually increase it to a total of 3000 milliamp hours. So remember, we've already seen this type of circuit with one cell and 1.5 ohms. In fact, it's just over here. So we found 1.5 volts, 1.5 ohms, at a capacity of 1000 milliamp hours. That'll last for 1 hour. So it's the same circuit in this case. We've still got 1.5 volts, 1.5 ohms. It's still going to draw 1000 milliamps, but now our total capacity has increased threefold. It will now last 3 times as long as before. It's going to last for 3 hours. So hopefully that's pretty basic. When you put cells in series, you increase the total voltage. So 1.5 plus 1.5 plus 1.5 in series gives us 4.5. However, we don't increase the current capability or capacity whatsoever. In parallel, it's the direct opposite. You connect them in parallel, you don't increase the voltage in any way, but now you increase the total capacity. Because if you like, what you can do is, have a look at this one. The current going through there is going to get some from here, it's going to get some from here, and it's going to get some from there. No one single cell has to provide all of that 1000 milliamps. So we're actually going to get a third from this guy, a third from this guy, a third from this guy. Therefore, it's going to last 3 times as long, which is good news if you want it to last a long time. So that brings us to this part. What happens if we combine them in series and parallel, which is what this thing is doing? Well, a lot of laptop battery packs or remote control car type battery packs and other things as well, they connect them together in a combination of series and parallel. So it's got here, or I've got a picture right up here, an old laptop battery pack with cells connected in series and parallel. So it's got right here, remember that when we place cells in series, we increase the total voltage. When we place them in parallel, we increase the total current capacity. This particular one that I've drawn right here, this group of cells will give us 4.5 volts because we've got 3 connected in series. And then we get those 3 in series, and then we copy and paste it 3 times. And now we've got them in parallel. So remember, in series you only increase the voltage, so it's 4.5 volts, but you don't increase the current. To increase the total current capacity, you've then got to do that again in parallel, and then in this case again a third time, to give you a total of 3000 milliamp hour capacity. So you may have seen stamped on battery packs before, it might have stamped on there something like, well, 4.5 volts, 3000 mAh. So in this case, if that battery pack was made from these, we would need to get 3 of them connected in series, and then copy and paste that another couple of times to give us 3 in parallel. That would now be rated at 4.5 volts, 3000 milliamp hour. Alright. Okay, so there are many different types of cells in all sorts of sizes, materials and chemical makeup, as I was saying before. These give us all sorts of voltages and current capacities. However, we calculate the total voltage and total current capacity the same no matter what sort of cells we are using. So these ones are 1.5 volts because of the makeup of the chemicals in there and the type of metals I've got in there. This one is made of different materials, and it's rated at 1.2 volts. So if we have a look at these ones, if we get 4 of them connected in series, it means we go 1.2 plus 1.2 plus 1.2 plus 1.2 is 4.8 volts. The current capacity of each cell is 2500 milliamps. So we've copied it and we've pasted it again, and now we've got 2 of them in parallel. So our total milliamp hour, so TMAH, total milliamp hour capacity, is 2500 plus 2500 to give us 5000 mAh. So stamped on this battery pack would be 4.8 volts and 5000 mAh, which is a pretty good battery pack. What about another example? Well, this particular guy, that's actually a 3.7 volt cell. So if we got a couple of 3.7 volt cells, put them in series, we're going to get 3.7 plus 3.7, which is 7.4 volts total. And each one of these are rated at 800 milliamp hour. So pretty small capacity compared to the other ones. But we've copied it and we've pasted it. So we've got the sets of 4 in parallel. So this time we're going to go 800 milliamp hour plus 800 plus 800 plus 800 gives us 3200 milliamp hour capacity. If we were to put another one in parallel again, it would go to 4000 milliamp hour. So we connect them in series and parallel, series to increase the voltage, parallel to increase the total current capacity.